All right, so let's talk about graphing some of these two variable functions here. Now this is one where we've kind of talked about it a little bit already, or we know what these are, because if we kind of rearrange things and think about, you know, this is z equals 4 minus x minus 2y. The ones we've talked about before on this actually have had where the x, y, and z are on the same side. So if I pull those x's and y terms over to this side, I mean, this is, you won't have to necessarily do this, but does that remind you of anything then? It's a plane, right? Yeah, so if you've got z, of course z is the first, but if the x and the y both are like this to the first power, like that, whether it's positive x or negative x or positive or negative y, that's a plane. And we haven't really graphed any of those yet, but that's what we're going to do here. But just recognizing, yeah, first of all, if you've got x to the first, y to the first in two variables like that, that's just going to be a plane, flat surface. All right, so the question then is how are we going to graph it? Well, it, as you know, gets a little tricky in 3 dimensions, but here's one thing we can do for planes. What they suggest is graph the intercepts, the x and y and z intercept for planes. So the x-intercept, of course, is when x is 0, z is 0. So that would be what? 0 equals 4 minus x minus 0. So that would be x is 4, would be my x-intercept. Or, in other words, 4, 0, 0, 0.5. Y-intercept, same deal, except the x and the z is 0, so see, what will that be? 2y equals 4, that's y equals 2, so that would be 0, 2, 0 for my y-intercept, and then the z-intercept, last but not least, z would equal 4 minus 0, so that's also z equals 4. So that's another point though, 0, 0, 4. All right, so those are fairly nice. If we put those then on the x, y, z coordinate system here, 3 dimensions. So 1, 2, 3, 4, 0, 0 around the x-axis, 0, 2, 0 on the y-axis, and then 0, 0, 4 on the z-axis. If you connect those, this isn't the whole graph, but it kind of gives you a little bit of perspective maybe. You kind of see, that's the plane in the first octant, because there's 8 different regions of your x, y, z coordinate system, but this gives the graph in the first octant, the plane in the first octant. And hopefully there you can kind of see it is angled there. I mean, you have to use a little bit of your visualization skills there a little bit, but you can kind of see it's at an angle here. Technically speaking, though, the graph of this is then, you know, all points parallel to that, or however you want to say it. I mean, it extends out from that in all directions. You know what I'm saying? It keeps going into the other octants. But that's just a nice way of showing at least part of it. Good part of it. So let's see what this one looks like, just to kind of compare and contrast. All right, so f of xy equals 8 minus 2x plus 4y. Also a plane, right? And then our intercepts, what would our intercepts be there? Well, we'd have, if the y and the z are zeros, what have we got? 4, again, 4, 0, 0, is that right? And then when the x and the z are 0, the y-intercept, well, that'd be -2, wouldn't it? And then the x is 0, y is 0, we got the z-intercept is 8. Right, you with me there? Does that sound right? So, here's what I'd show then. All right, so we got the x-intercept is 4, so again 4 units along the x-axis, -2, all right, and so on the y-axis we're actually going to back up a little bit, -1, -2, so be right there on the y-axis, and then 8 for the z-intercept. Yeah, so actually this one wouldn't be first octant there, but you can kind of see, hopefully, there. You got the little triangle, the angle of it, and so that gives me one part of it. Like I said, that one's not in the first octant, actually. But, yeah, you kind of can get a feel for it. It's at a different angle than this one, right? So, so get your intercepts and then connect the dots and get a feel for where the plane though extends. It would extend down and then out and back from that. Is that right? Okay. Now this one is also a little different. See what you think on this one. So this is 3. F of xy equals -2y plus 3, or 3 minus 2y. That one is different because we're missing an x, aren't we? It's really just in one variable, but it is a 2-variable function. So let's think about that. It's still a plane, right? Because it's still just y to the first, so there's no nothing more to it than that. So it's a plane. However, in this particular case, well, if we do our thing, the intercepts here that we could get, well, we could get, if y is 0 and z is 0, yeah, we've got, what's the x? Well, you can't solve for x there. X can be anything. So, you know, we could do z is 0, x is 0, and get solve for y. The y would be what? So that'd be 0 equals -2y plus 3. So 2y equals 3. So that's 3/2. So we could do that even though we're not plugging in an x value. And then of course, x is 0, y is 0, that would be 3. So other than, yeah, we can't really get an x-intercept out of that because you can't solve for x in the case. Matter of fact, if we give you, there is no x-intercept, well, yeah. All right, so let's think about it. So we've got 3, 0, 0, and then 0, 3/2, 0. Yeah, the deal on this one is the x can be anything. It's just that the z has to equal negative 2y plus 3. Well, if you think about that, that's just a line, right? If you're just thinking about in the yz plane, that's just a line. So yeah, you've got this line, but x can be anything. So this particular one is just when, that would be when x is 0. So if I move to say x equals 1, that would be another line, right? X could be 1. So it's just another line here. But it's the same line. So here's kind of what it works out to be. It's a plane where you get all these z equals negative 2y plus 3 lines. Kind of angled at that same angle there. I probably should have moved it a little better. Try that again. Make it parallel to the. Make this kind of run parallel to the x-axis since x can be anything. Get in that one. We're talking z equals y squared. I mean that, which we know that is obviously a parabola. So this is y, this is z. So you got a parabola, right? Well, the yz plane, that's when x is 0. All right, when x is 1, it's still z equals y squared. And so for x equals 1, we'd also have a parabola. So let's kind of put that together. So on the yz plane, we know we've got this parabola. When x is 1, we also have a parabola there. When x equals 2, we also have a parabola, z equals y squared there. It kind of gets cluttered pretty fast, but here's what it amounts to. We kind of make these a little taller. Going to keep going on past a negative. So let's see. All right, so we've got this, and then this comes around here. See that? Yeah, so we probably don't really see that. So each you kind of get this sheet kind of bent around in a sort of in a parabola shape, right? Where the cross section is a parabola. Yeah, it gets fun to draw on me, so do your best. Okay. All right, now, here's another, and sort of did it there, but not really. sometimes we can use what are called level curves. They call them level curves here. So what a level curve is, it's the graph of z equals f of x, y, taking fixed values of z. In other words, taking z equals some constant k. So it's just thinking about the graph of z equals f of x, y, taking fixed values of z, or z equals a constant. For example, f of x, y equals x squared plus y squared. All right, so here's what I'm going to do. I'm going to do level curves for k equals, and we'll see why I picked these in particular here. We don't have to necessarily pick nice numbers, but in this case it may be helpful. All right, so z equals 0, 1, 4, and 9. Okay, so if z equals 0, what we've got is 0 equals x squared plus y squared. Well, that's not a very interesting equation because the only solution would be what? 0, 0. Right? It's 1 point. That's the only way you get x squared plus y squared equals 0. All right, but let's do, whoops, that was k equals 0, which means z equals 0. All right, so then let's do k equals 1, which means z equals 1, so that's 1 equals x squared plus y squared. Okay, so that's a little more interesting. And so we're just going to graph our level curves here. So when you're talking level curves, you're just talking in xy plane. So the first one is k equals 0, which is just one solution. The second one, all right, so what do we got there? Well, that's a circle, center 0, 0, radius 1, right? So the level curve, when k equals 1, that's just our unit circle radius 1. All right, k equals, so I jumped to 4. You can see why I jumped to 4 now, because that'll give me nice radii, nice radius. All right, so k equals 4, that would mean z equals 4, so that's 4 equals x squared plus y squared. That's circle, radius 2, center 0, 0. Oops, so I'm working my way out. So yeah, you get the picture here. The next one I chose was k equals 9, so that would be the radius 3 circle. So one more out. So those are the level curves. Now, what that gives you for, all right, so now let's think about the actual graph of f of x, y equals x squared plus y squared. Well, what these level curves give, oh, by the way, another term they use here is when you get these level curves all in one graph, I forgot to label this one, k equals 3 there. That's also called the contour map. So a contour map is just XY graph with different level curves on it. Basically what it is. All right, so what does this level curve provide me? Well, what these level curves are, they're basically slices of your graph. So the level curves are the slices of the graph. And it's each, let's draw my x-axis too sharp there. So let's put them on here. Okay, so this gives me, each one of these give me a slice. Now, the slice, so what the k equals 1 slice, for example, gives me, that gives me the slice for z equals 1, right? So this is what it would look like at z equals 1. If I slice this graph at z equals 1, then I'm looking at a circle, radius 1. So if I put that on here, of course it's, the xy plane now is at a different angle, if you will. So, but it's a circle. Kind of goes around the z-axis right there. Well, if I move out to k equals 2 level curve, that's the slice at z equals 2. So at z equals 2, z equals 4. Whoops, I missed these, didn't I? This is k equals 4 and this is k equals 9. I messed those up. Sorry about that. K equals 4, k equals 9. I mislabeled my level curves there. Because that's significant because that's where I go in the z-axis. So k equals 4 is where I do the radius 2 circle. So be sure to clean that up on you got your notes there. So at z equals 4, I've got this radius 2 circle. So it's a circle kind of centered up here at the z-axis, but it's radius 2. And then I have to go up to 9, and plan this out too well, didn't I? Get rid of that wordage there. So I'll go up to 9, which we'll say is there. And what I have there, slice-wise, is another circle, but it's radius 3, so it's a little bigger. Now, I didn't do the 0 one, but what have I got at 0? Level 0? 0. Okay. Now, if I kind of connect these up, because if you think about it, the slices, what the slices are doing, they're just progressing out. And so if I did a slice here, it'd be just a little bit smaller. This one would be a little bit bigger than that, a little bit smaller than that. So this is just progressing out, isn't it? And so you get kind of an idea here. It's going to be a kind of a cone shape. It's a paraboloid, actually, is what the term for it is. All right, so that can be helpful to graphing some of these two-variable functions. Let's try that. All right. So let's draw a contour map. And then graph. So here it is. F of xy equals ln x squared plus y. Well, like I said, a contour map, that's just putting different level curves in a XY graph. Now, in this particular case, it doesn't look like, doesn't look like there's anything in particular I'd want X and Y be. So let's just start with K equals 0, see where that takes us. So if K equals 0, that means Z equals 0, so the equation is this. Now, that is probably something you're not that familiar with, graph-wise. So let's change this to a Y equals equation. You know what I'm saying? Solve that for Y. How would I solve that for Y? Exponentiate both sides, E both sides, because what happens? The E and the ln cancel one another out, so we wind up with 1 equals x squared plus y. Solve for y, so that would be 1 minus x squared equals y. That I'm familiar with, right? That's upside down parabola, shifted 1 unit up. Let's put it on over here so I can do some more mappings here. So now remember, when I'm doing my level curves graphing, I'm just graphing those in X, Y. So yeah, like I said, that's just an upside down parabola, 1 unit up. So that's for K equals 0. All right, what do we got for K equals 1? Well, that would be 1 equals 1. So ln of x squared plus y equals 1, which would be what? E to the 1 equals x squared plus y. So subtract the x squared, so the e minus x squared equals y. What's that? Well, that's the upside down parabola shifted e, which e is about 2.72. So at k equals 1, it's shifted up 2.72. Let's put it right about there. But it's the same shape. So that's for k equals 1. K equals 2. We'd have 2 equals ln's. Kind of gets repetitive after a while, but so that would be e squared equals x squared plus y, wouldn't it? So that's e squared minus x squared equals y. Let's see, e squared, what's e squared about? 2.72 squared. It's not quite 9. What is it? Somebody got it for me, approximately? E squared?
7.38.
7.38. Okay, so it's up about, what do we got there? That's one, whoops, I put that up a little too far, didn't I? This is just 2.72. Which is right here. So that's about 7.38. So 1, 2, 3, 4, 5, 6, 7.3. Okay. So right about there. Same basic shape. Okay. All right. Well, let's go to the graph. So let's graph this in our 3 dimensions. See what we can tell about this thing. So again, what these give me are slices for that particular z value. So K equals 0, that's telling me what it looks like when z equals 0. So if z equals 0, I've got this parabola in the xy plane, if you will. Well, what it is, it's at z equals 0, it's shifted, it's shifted up in the y 1 unit, and also it's shifted in the, so the vertex is there at, it's on the y-axis, the vertex is. The vertex on the y-axis, but it's shifted in the y direction here. So at z equals 0, I'm talking grab like this. Kind of like that. Oops, it goes along the, sorry, it goes along the x-axis. I confused myself. All right. So it's equals 0, so that's down here. Yeah, that's right. That right. Yeah, it crosses your x-axis in two places, so that kind of gets it. Now we go up to k equals 1, which is z equals 1. So at the height z equals 1, stays there, we've got another parabola. But now the parabola is shifted in the y direction 2.72 approximately units. So, so if you're thinking here, the y-axis goes this way, so it's further out here along the y-axis. You know what I'm saying? So 1, 2.7. So here's my parabola. It's back a little bit from that. Now at k equals 2, that would be z equals 2. So up here at this level now, it's shifted even further back on the y, so it's further back about 7.5. So along the y-axis this way, so it's about 7.5. So you got this. Now, this one's different than our previous one there, because unlike the previous one where z could not be, we had z f of x, y equals x squared plus y squared. Well, you're never going to get z can't be less than 0. Z's got to be greater than or equal to 0. Here, can z be a negative? Sure can. So let's think about that. What happens here? So if I do a level curve, say at -2, let's see what happens. Well, that would put us -2 equals ln of x squared plus y. Both sides, you got e to the -2 equals x squared plus y, so that would be e to the -2 minus x squared equals y, and that's approximately, somebody get that for me, what's e to the -2? It's 1 divided by e squared, so 1 divided by 7, a seventh, something like that. And so it's not too far down here. So here's, it shifted up just a little bit. 7. So that's for k equals -2. Well, over here then, if I look at that, so that's the z is -2. So 1, 2, so it's z equals -2. My shift is still in the positive y, but it's not by very much. Okay. So here's the thing. What I would do here is let's connect these vertices, I guess you could call them. And then let's kind of make these about the same here. And these about the same here, so here's kind of what I get. Hope he's all right. What you hopefully kind of see there, yeah, is you get these little